index core in Lucene. Now we are focusing on index core. Index core is the direct focus when manipulating file indexes. Now we are focusing on Lucene index. Indexer org.apache.lucene.index provides two primary classes: index writer, which creates and adds documents to indices, and index reader, which accesses the data in the index. Here you can see two main processing flow: index update and index search. Document indexing, here the given a document, add it into the index, and document retrieval for a given query, retrieve the most relevant document from the index. Here you can see raw data and parser in index update. Doc is connected to fields, and fields are connected to terms, and you can see the analyzer here. Lowercase removes stop words stemming, and index writer is connected to inverted index, and you can see the directory here, and index reader is connected to the inverted index. Here you can see statistics, delete, undelete docs, and inverted index is connected to the index searcher. Here you can see, and you can see the hits also, and filtered by Boolean model, scored by a vector space model, cosine it's just model cosine distance of query and doc, and controlled by boosting. Here query language, and here you can see the query parser. You can see the term query. You can see the query here: term query, price query, Boolean query, range query. Query is connected to the fields, and fields are connected to the term. You can see analyzer here, and you can see the index searcher here. Here you can see Lucene indexing mechanism. Here to index data with Lucene, first of all we must convert it to a stream of plain text tokens. Therefore, other patterns of files must be converted into text before being indexed. Secondly, create a document object with its relevant field object, then call the method add document. To store the data for indexing. Next, use the specified analyzer to tokenize every word of indexes so that the data stream can be more suitable to be indexed. Last but not least, write the result back to the index files. The process of building full text indices is presented in this figure. Here you can see files to be indexed. Here .html, .text, .doc, .pdf. These are connected to document processing. Here you can see file patterns to be converted and add document. Document processing is connected to language analyzer. Language analyzer is connected to index files. Here you can see Lucene based full text search contains index management and search index. Its data handling process is like this figure. Here being index document is connected to accidents analyzing logic. Text stream is passed from being index document to accidents analyzing logic. Query sentences are connected to accidents analyzing logic. Text stream is passed from query sentences to accident analyzing logic. Accidents analyzing logic is connected to construct index logic. Meta word stream is passed from accidents analyzing logic to construct index logic. Accident analysis logic is connected to query sentences accidents analysis logic. Meta word stem is passed from accidents analyzing logic to query sentences accidents analyzing logic. And query sentences accidents analyzing logic is connected to index query logic. Query sentences object stream is passed from query sentences accidents analysis logic to index document query logic. Construct index logic is connected to storage abstract. Byte stream is passed from construct index logic to storage abstract. Index document is connected to storage abstract. Byte stream is passed from index document to storage abstract. Storage abstract is connected to index query index document query logic. Byte stream is passed from index storage abstracts to index document query logic. Index document query logic is connected to estimate and composer. Meta word stem is passed from index document query logic to estimate and composer logic. Estimate and composer logic is connected to query result. Text stream is passed from estimate and composer logic to query results. Here you can see inverted index implementation. First we can discuss about index structure. Both document and query is represented as a bag of words. In Apache Lucene, document is the basic unit for storage and retrieval. A document contains multiple fields, also called zones. Each field contains multiple terms equivalent to words. To control how the document will be indexed across its containing fields, a field can be declared in multiple ways to specify whether it should be analyzed. Pre-processing step during index participate in the index or stored in the case it need to be returned in the query result. Keyword not analyzed, indexed, stored. Unindexed, not analyzed, not indexed, stored. Unsorted, analyzed, indexed, not sorted. Text analyzed, indexed, sorted. Stored. In unstored, analyzed, indexed, and not stored. Inverted index is a core structure of the storage. It is organized as an inverted manner from terms to the list of documents which contains the terms. The list known as posting list is ordered by the global ordering, typically by document ID. To enable faster retrieval, the list is not just a single list but a hierarchy of skip list. This data structure is illustration here based on Lucene's implementation. It is stored on disk as segmented files, which will be both to memory during processing. Here the fields are connected to terms. Terms are connected to document frequencies, and terms are connected to documents. A term is connected to document, and document is connected to positions here list, and it has a term frequency. and document is connected to another document like that. Likewise here, and in index segment Lucene implementation, field definitions are here, field whether index and stored and offset, and this this record is connected to, this line is connected to field here, posting list, field term doc frequency, offset here 2, and it's connected to frequency here as a doc frequency, and offset here here it is 3, and this is connected to position here 1920 here. Here you can see the additional forward index. The whole index contain an additional forward index as here. Here the document is connected to fields, and fields connected to terms, and term you can see the term frequency here, and terms is connected to positions, and here you can see other documents. Here you can see indexing diagram. In Lucene index algorithm, two basic algorithms, one make an index for a single document, and two match a set of indices. Incremental algorithm maintain stack of segmented indices, create index for each incoming document, push new indices into the stack, and then merge. Optimization single doc indices kept in RAM saves system calls. Here b equal 3 and 11 documents indexed. Stack has 4 indices. Gray indices have been deleted. Five mergers have occurred here. You can see the document indexing here. In document indexing, the document in its raw form is extracted from a data adapter. This can be making an web API to retrieve some text output, or crawl a web page, or receiving an HTTP document upload. This can be done in a batch or online manner. When the index processing starts, it presses each raw document and analyzes its content. Typical steps include tokenize the document, break down into words, lowercase each word to make it non-case sensitive, but need to be careful with names and abbreviations. Remove stop words, take out high frequency words like the, but need to careful with phrases. Stemming, normalize different form of same word. For example, reduce run, running, ran into run. Synonym handling, this can be done in 2 ways. Either expand the term to include synonyms, its synonyms, that is, if the term is huge, add gigantic and big, or reduce the term to a normalized synonym, that is, if the term is gigantic or huge, changing it to big. At this point, the document is composed with multiple terms. Document equals term 1, term 2, etc. Optionally, the terms can be further combined into n-grams. After that, we count the term frequency with this document. For example, in a bigram expansion, the document will become document 1, doc 1 implies term 1 colon 5, term 2 colon 8, term 3 colon 4, term 1 underscore 2 colon 3, term 2 underscore 3 colon 1. We may compute a static score based on some measure of the quality of the document. After that, we insert the document into posting list. If it exists, otherwise create a new posting list for each terms of n grams. This will create an inverted list structure. There is a boost factor that can be set to the document or field. The boosting factor effectively multiply the term frequency, which effectively affecting the importance of the document or field. Document can be added to the index in one of the following ways: inserted, modified, and deleted. Typically, the document will first added to the memory buffer, which is organized as an inverted index in RAM. When this is a document insertion, it goes through the normal indexing process to analyze the document and build an inverted index list in RAM. When this is a document deletion, the client request only contains the doc ID. It reflects the forward index to extract the document content, then goes through the normal indexing process to analyze the document, build an inverted list. But in this case, the doc object in the inverted list labeled as deleted. When this is a document update, the client request contain the modified document. It is handled as a deletion followed by an insertion, which means the system first fetch the old document from the forward index to build an inverted list with nodes marked deleted, and then build the new inverted list from the modified document. For example, if doc1 equal AB is update to AC, then the posting list will be A colon doc1 deleted implies doc1, B colon doc1 deleted, C colon doc1. After collapsing A, the posting list will be A colon doc1, B colon doc1 deleted, C colon doc1. As more and more documents are inserted into the memory buffer, it will become full and will be flushed to a segment file on the disk. In the background, when M segments have been accumulated, Lucene merges them into bigger segment files. Notice that the size of the segment files at each level is exponentially increased. M to the power 2, M to the power 3. This maintains the number of segment files that need to be searched per query to be at the big O log n complexity, where n is the number of documents in the index. Lucene also provides explicit optimize call that merges all segment files into one. Here let's details a bit on the merging process. Since the posting list is already vertically ordered by terms, and horizontally ordered by doc ID, merging two segment files S1 and S2 is basically as follows. Walk through the list of both S1 and S2 together in the walk the posting list from both S1 and S2 together in shorter term order. For those non-common terms that appeared in one of S1 or S2 but not both, write out the posting list to a new segment S3. Until we find a common term T, we merge the corresponding posting list from these two segments. Since both lists are sorted by doc ID, we just walk through both posting lists to write out the doc object to a new posting list. When both posting lists have same doc, which is the case when the document is updated or deleted, we pick the latest doc based on the time order. Finally, doc frequency of each posting list of the corresponding term will be computed. Here you can see merge factor equal m and can explicitly call index writer dot optimize to merge all segment into one single documents. Here you can see doc1, doc2, doc3 is connected to memory buffer posting list. After m documents are added, write out the posting list to the index segment here, level 1, and clear the memory buffer. Here the memory buffer is connected to index segment, here level 1, and index segments of level 1 are connected to index segments of level 2. If there is already m segments at level 1, step 1, merge m segments level 1 to a new segment of level 2 and clear the m segments of level 1. And here you can see whole the index of m documents here and whole the index of m to the power 2 documents here, and index segments of level 2 are connected to index segments of level 3 here, and here holds the index of m to the power 3 documents here. Here in for large, here you can see document partitioning. For large corpus like web documents, the index is typically distributed across multiple machines. There are two models of distribution: term partitioning and document partitioning. In document partitioning, documents are randomly spread across different partitions where the index is built. In term partitioning, the terms are spread across different partitions. We will discuss the document partitioning as it's the most commonly used. Distributed index provided by other technologies that is built on Lucene, such as Elasticsearch. A typical setting is as follows. In this setting, machines are organized as columns and rows. Each column represents a partition of documents, while each row represents a replica of whole corpus. During document indexing, first row of the machine is randomly selected and will be allocated for building the index. When the new document is crawled, a column machine from the selected row is randomly picked to host the document. The document will be sent to this machine where the index is being built. Updated index will be later propagated to other rows of replicas. During document retrieval, the first row of the replica machine is selected. The client query will then broadcast to the every column machine of the selected row. Each machine will perform the search on its local index and return the top M elements to the query processor, which will consolidate the result before sending back to the client. Notice that k divided p less than m less than k, where k is the top k documents the client expects and p is the number of columns of the machine. Notice that m is the parameter that needed to be turned. One caveat of this distributed index is that as the posting list is split horizontally across partitions, we lost the global view of IDF value, without which the machine is unable to calculate TF-IDF score. There are two ways to mitigate that. Do nothing. Here we assume the document is evenly spread across different partitions to the local IDF represent a good ratio of the actual IDF. 2 extra round trip. In the first round, query is broadcast to every column of the return to its local IDF. The query processor will collected the IDF response and compute the sum of the IDF. In the second round, it's broadcast the query along with the IDF sum to each column of the machine, which will compute the local score based on the sum. Here you can see term partitioning, machine T1, term 1, term 2, machine T2, term 3, term 4, term 5. And here you can see machine D1, doc 1, doc 2. Here machine D2, this is document partitioning. Machine D2, doc 3, doc 4, doc 5. Here machine D3, doc 6, doc 7. This is about distributed index here. And here you can see a client query and pick a random row and scatter together, and this is connected to partition 1 replica, partition 2 replica, partition 3 replica. Here you can see the row 1 and row 2. Here you can see the crawler randomly pick one, and here you can see the indices, and here you can see the inverted index. Here this inverted index connected to this one, and here this inverted index is connected to this one of the row 1, and this here the partition 3, the inverted index is connected to this one. Here you can see the structure of Lucene index. The Lucene index is stored in a single directory in the file system on a hard disk. The core element of the Lucene index are segments, documents, fields, and terms. In Lucene index, every index consists of one or more segments. Each segment contains one or more documents. Each document has one or more fields, and each field contains one or more terms. Each term is a pair of string representing a field name and a value. So a segment consists of series of files. Pictorially, the entire structure of a Lucene index can be represented as shown in this figure here. Exact number of files that constitute each segment varies from index to index and depends on the number of fields that the index contains. All files belonging to the same segment share a common prefix and differ in the suffix. One can think of segment as a subindex, although each segment is not fully independent index. Here you can see the index here. Segments is inside index, and document or documents are inside segments, and here the in segment, and fields. So fields are in documents, and terms are in fields, and pair of strings are in term. Field name and field value are in pair of strings. Now we are considering Lucene index. A Lucene index is an inverted index. An inverted index means that the content of the documents that are analyzed has their important terms indexed as a pair consisting of a field name and a field value. A field contains many terms that point to the corresponding document. To summarize, an inverted index makes the process of retrieving documents from a system breeze. Finally, the documents are searched in the fields and their values. A Lucene index consists of many segments. A segment is created every time when new document is created and indexed. Hence, each segment has many documents stored in it. The document consists of index fields. An index field is a pair consisting of a field name and field value pairs. Fields are used for calculating weights and ranking each search result. Here you can see the index is connected to segments. Segments is connected to documents, and document is connected to here fields. Here you can see the Lucene indexing architecture. The entire indexing procedure can be summarized as shown in this figure. Here the source data is connected to source specific parser, and it is connected to PDF parser, HTML parser, XML parser, user defined parser. Source specific parser is connected to analyzer, and it is connected to white space, simple, standard, etc. And analyzer is connected to index. Here you can see the basic internal structure of an index. This figure shows the basic internal structure of an index. The data in a segment is represented abstractly rather than as a realistic representation of actual data structure. Index. This is similar conceptually to database table, but differ in some important ways. The table in traditional relational database or NoSQL database needs to at least have its scheme defined when it is created. There are some clear constraints on the definition of the primary key, columns, and the like. However, there are no such constraint in Lucene index. Lucene index can be understood as a document folder. You can put a new document into the folder, or you can take one out. But if you want to modify one of the document, you must first take it out, modify it, and then put it back in the folder. You can put all sort of document in the folder, and Lucene can index the document whatever the content. Document similar to a row in a relational database. So a document in a document database, an index can contain multiple documents. A document written into an index is assigned a unique ID. That is the sequence number, more usually called doc ID. Sequence numbers are doc ID field. One document is made up of one or more fields. A field is the smallest definable unit in data index in Lucene. Lucene provides many different types of field, including string field, text field, and numeric data values field. Lucene determines the type of indexing, such as inverted index, stored field, doc values, or n-dimensional, to use for the data depending on the field type, the type of the field type. Field and field type field type. The term and term dictionary, smallest unit of index and the search in Lucene. Field consists of one or more terms. The term is produced when a field is put through an analyzer, tokenizer. The term dictionary is the basic index used to perform conditional searches on terms. Segment. An index is composed of one or more sub-indexes. A sub-index is called segment. The conceptual design of segment in Lucene is similar to LSM, but there are some differences. They inherit the data writing advantage of LSM, but only provide near real-time but not real-time queries. When Lucene writes the data in first write to a in-memory buffer similar to memtable in LSM but not readable. When the data in the buffer reaches a certain amount, it will be flushed to become a segment. Every segment has its own independent index and are independently searchable, but the data can never be changed. This scheme prevents from random writes. Data is written as batch or as an append or achieves a high throughput. The documents written in segment cannot be modified, but they can be deleted. The deletion method does not change the file in its original internal location, but the doc ID of the document to be deleted is saved by the another file to ensure that the data file cannot be modified. Index queries need to query multiple segments and merge the result, as well as handling deleted document. In order to optimize queries, Lucene has a policy to merge multiple segments, and in this regard is similar to LSM's merge of SS table. Before segments are flushed or committed, data is stored in a memory and is unsearchable. There is another reason why Lucene is said to provide near real-time and not real-time queries. After reading the code, the reason for this is the searching of data in Lucene relies on the index setup. For example, the inverted index relies on term dictionary, and the data index in Lucene is set up during segment flush and not in the real time. The purpose of this is to set up the most efficient index. Naturally, it can introduce another index mechanism that set up the index in real time as it is written, but implementation of such mechanism would differ from the current index in the segment, needing the introduction of extra index at the right time, and an extra query mechanism involving some degree of complexity. Sequence number. A sequence number is called doc ID. Is an important concept of Lucene. The database uniquely identifies a row using primary key, while Lucene index uniquely identifies the files doc by its doc ID. However, the following points should be kept in mind. One, the doc ID is not actually unique to index, but is unique to a segment. Lucene does this mainly to optimize the writing and compression. Since it is only unique to a segment, how can a doc be uniquely identified at the index level? The solution is simple. The segments are ordered. To take simple example, an index has two segments, and each segment has 100 docs. Respectively, the doc IDs in segment are 0 to 100, but when they are converted to the index level, the range of doc IDs in the second segment is converted to 100 to 200. Doc ID is unique within a segment, numbered progressively from 0, but this does not mean the doc IDs are continuous. When a doc is deleted, there is a gap. 3. The doc ID corresponding to a document can change, usually when segments are merged. The inverted index, a very core of Lucene, is essentially list mapping each term to the doc IDs of the document containing the term. So when Lucene is searching internally, it makes a two-phase query. First phase is to list the doc IDs found to contain the given term. So when the Lucene is searched, and the second phase is to find the doc based on the doc ID. Lucene provides functionality to search by term as well as to query on the basis of doc ID. Doc ID is basically an int32 value starting from 0, which is an important optimization. Also reflected in the compression and query efficiently. This includes such optimization as a delta policy for data compression, zigzag code, skip list used in inverted index list. These are here you can see doc in-memory buffer segments, and segments are in index. Doc is connected to in-memory buffer via add document, and in-memory buffer is connected to segments via flush. Here the as an example, here segment 0, 1 and 2 is connected to segment 4 via merge. Here the in a segment you can see doc IDs and doc, and here the as an example here the doc ID 4, the doc 4 is connected to here doc 4 here. It has fields and values. Here you can see the basic relationships between different types of fields and fields in Lucene. Lucene supports many types of field, and each type of field determines the supported data type and index modes. Currently, the supported field types include long point, text field, string field, and numeric doc values field. This figure shows the basic relationship between different types of field in Lucene. All field types inherit from the class field. The field has three main attributes: name, string, and field data, bytes ref, and type, field type. Attribute name is the name of the field. Field's data is the name of the value. The value of all types fields are ultimately represented as binary type byte streams. The attribute type is the type of field which determines how field is indexed. Field type is an important class containing many important attributes. The value of these attributes decide how the field is indexed. Lucene provides many types of fields. There are two essential differences. First difference is the different types of values in the field define different conversion methods, and the second is the defining combination of different values in different attributes of field types. In this mode, you can customize types using custom data and combining the index parameters in the field type. You only have to understand the specific meaning of each attributes in the field type to know what index modes Lucene can provide. Let's look at them one by one. Stored indicates whether to save the field. If false, Lucene does not store the value of the field, and document returned in the query result will only contain saved field. Tokenized represent whether or not to tokenize. In Lucene, only a text field needs to be tokenized. Term vector. Here we explain the concept of term vector, that simply put, the term vector saves all information related to term, include term value, frequencies, positions. It is per document inverted index, and provide functionality to find all term information in the document according to doc ID. It is not recommended to enable term vector for short fields, because all the term information can be obtained by tokenizing once again. However, it is recommended to enable term vector for longer fields, so fields with the high cost tokenization. There are two main uses of term vector. First is keyword highlighting, and the other one is similarity matching between documents, more like this. Omit norms. Norm stand for normalization. Lucene enables every field in every document to have normalization factor saved. This is a coefficient related to scoring during searches. It only takes 1 byte to save the norms, but separate norm is saved in every field of every document, and every piece of norms data is loading into memory. So enabling norms consumes additional storage space and memory. But if you disable norms, you cannot use index time boosting. Elasticsearch officially recommends using query time boosting instead than length normalization. Index options. Lucene provides 5 optional parameters for inverted index: none, docs, doc and fix, docs and fix and positions, and doc and fix and positions and offsets, which are used to select whether the field needs to be indexed and what content to index. Doc values type. Doc value is an forwarded index introduced in Lucene 4.0 doc ID to field column store, greatly enhancing the efficiency of sorting, faceting, and aggregation. Doc values is a storage structure with a strong schema, so all fields with doc values enabled must have exactly the same type. Currently, Lucene only provides 5 types of numeric, binary, sorted numeric, and sorted set. Dimension. Lucene supports indexing of multidimensional data, employing special indexing to optimize querying of multidimensional data. Most typical usage scenario of this type of data is the index geographical location. This is an indexing method generally used for latitude, longitude data. Here you can see the subtypes, fields, long point, subtype field, long point, string field, text field, numeric, doc value field, and here you can see the string name, byte ref, field data, field type. See the field types: stored, tokenized, term vector. Here with under term, store term vector, store term vector, offset, store term vector, position, store term vector, payload, and omit norms, index options, doc value types, and dimensions. Dimension count, dimension num bytes. Here you can see the structure of Lucene segment. Here the Lucene 4.0 we are considering. Lucene uses a well-known inverted index representation with additional functionality of keeping adjacent non-inverted data on per document basis. Both in-flight and persistent data uses variety of encoding schema that affect the size of the index's data and the cost of data compression. Lucene uses pluggable mechanism for data coding and for actual storage of index data, directory API, Incremental updates are supported and stored in indexed extent, refers to as segments that periodically merge into larger segment to minimize the total number of index parts. The document model the document model, the documents are modeled in Lucene as a flat ordered list of fields with the content. Fields have name and content data, float weight used for scoring, and loose letter for scoring, and the other attributes depending on the type, which together determine how the content is processed and represented in the index. There can be multiple fields in the same name in a document. In which they can or will be processed sequentially. Documents are not required to have a unique identifier, though they often carry a field with this role for application level unique key lookup. In the process of indexing, document are assigned internal integer identifiers. Field types, there are two broad categories of fields in Lucene document. Those carry content to be inverted indexed field. And those which content of the to be stored as is the stored field. Fields may belong to either or both categories, for example with content both to be stored and inverted. Both index and stored fields can be submitted for storing and or indexing, but only stored fields can be retrieved. The inverted index can be accessed as and traverse being using a specialized API. Index fields can be provided in plain text, in which the case it will first pass through a text analysis pipeline, and it is or in its final form of a sequence for tokens of tokens with attributes, so-called token stream. Token streams are then inverted and added to the in-memory segments, which are periodically flushed and merged depending on the field options. Various token attributes such as positions, starting or coding offset or position payloads are also stored in the inverted data. It is possible, for example, to omit positional information while still storing the in-document terms frequencies. On per field basis, a variant of an index field is a field where the creation and storage of term frequency vectors are requested. In this case, the token stream is used also for building a small inverted index consisting of data from current field only, and this inverted data is then stored on the per document or per field basis. Term frequency vectors are particularly useful when they perform in document highlighting or relevance feedback, or when generating search result snippet region of the text that best matches the query terms. Stored fields are typically used for storing auxiliary per document data that is not searchable but would be cumbersome to obtain otherwise. For example, it would require retrieval from a separate system. This data is stored as byte arrays but can be manipulated through a more convenient API that present it as a UTF-8 strings, numbers, arrays, etc. Or optionally, it can be stored using strongly typed API, so-called doc values, that can use more optimized storage format. This kind of strongly typed storage is used for example to store per document per field weight, so-called norms, and they typically are responded to typically corresponded to field length normalization factor that affects scoring. Here you can see segment info, field info, live docs bit set, per document field data, per document inverted data in segment. Here the segment info, commit metadata, segment stats, and here then you can see field info, field metadata. Field info interacts with per document field data and per term inverted data. Stored values, term vectors in document frequencies plus positions. Scoring and scoring values, norms, are in per document field data. Term dictionary plus doc frequencies, and per document term frequencies and per position attributes are in per term inverted data. Here you can see a term dictionary plus doc and frequencies. Here more descriptive, and inside it there's a per document term frequencies, and inside it per position attributes. Here you can see live docs or bit set deletions. Here you can see indexing process in here we are considering Lucene 4.0. The resulting token stream is finally processed by indexing chain. And the supported attributes, term value, position, offset, and payload data are added to the respective posting list for each term. Term values don't have to be UTF-8 strings as in previous versions of Lucene. The version 4.0 fully supports arbitrarily byte array values as terms and can use custom comparators to define the sorting order of such terms. Also at this stage, documents are assigned to their internal document. Document identifiers, which are small sequential integers for efficient delta compression. These identifiers are ephemeral. They are used for identifying document data within a particular segment, so they naturally change after two or more segments are merged during index compaction. Here you can see the tokenizer. It is connected to field value, field 1, doc 1 are connected to here to the tokenizer. You can see term, position, offset, payload, and custom in tokenizer, and it is connected to token filters via token stream with modifiable attributes. Token filters are connected to document inverter. Here you can see the indexing chain and in-memory segment here. And a document inverter is connected to term vectors and posting list. Here you can see the term vectors, and here you can see the posting lists. Here the token filter is connected to document content via field 1 and field doc in this example. Via field 1 and doc 1. Now we are considering a prefix tree in spatial indexing. The spatial module is based on spatial 4.4J and Apache license library that provides implementation of various shapes such as points, rectangles, and circles, and additionally support polygons with an extra dependency. Spatial strategy is the core interface used to interact with spatial module index spatial data and perform spatial queries. Spatial strategy define the way to index and query based on shapes. From Lucene Java docs, the points defined by spatial strategy as follows. Can it fix more than one shape or field? What type of shapes to be indexed? What type of query shapes can be used, and what types of query operations are supported. This might vary per shape. Remember that the different shape is attempted to be indexed than what is defined by corresponding spatial strategy, and exception will be thrown. Prefix trees from the foundation of spatial index data structures in Lucene. Prefix trees act as a tree data structure where shapes are decomposed into strings. Each string representing a rectangular spatial region. This figure shows a prefix tree of words car, cat, do, and don. Car, cat, do, and don. Lucene defines an abstract class, a spatial prefix tree, which represent abstract representation of the prefix tree. This class defined all necessary methods such as getting the number of levels, getting a cell at level, and so on. There are that are required for working with prefix trees during searches. As the Lucene consists of two concrete implementation: spatial prefix tree, quad prefix tree, and geohash prefix tree. Here you can see root is connected to C, and C is connected to A, and A is connected to R, car, and then I is connected to end, car. Here C is connected to A, and A is connected to T, and it is connected to N, is cat. And here the root is connected to D, and do is connected to D is connected to O, and O is connected to N, and it's do. And here do is connected, D is connected to O, and O is connected to N, and N is connected to N, is done here. Here you can see a quad tree. A quad tree is a spatial data structure where each node has exactly 4 children. Quad tree splits a spatial dimension into 4 each time a new level is added to the tree. Quad trees are notable for two use properties. Higher level nodes of quad tree help representation of overall data in a less granular level. That is, a depth of detail stored in the top level is less than that stored in the leaf level nodes. Quad trees are great for searching two-dimensional spaces. For example, given a two-dimensional space, to find the point closest to the given coordinates, a simple traversal of quad tree will lead to the result. Here you can see a quad tree. Here root is connected to A here, and here is connected to node, and it's another connected to node, and this one is connected to B, C, D, and E. Here this one is connected to another node, then S, K, and L. Here this node is connected to G, H, I, and L. Oh, this one here. Here you can see a KD tree in spatial indexing. A KD tree is a space partitioning space partitioning tree that's allow splitting a plane of space into k-dimensional space. A KD tree is a binary tree which with each node representing a k-dimensional point. But put simply, given a collection of points, a range is split using an axis value. For example, if a node represents x-axis and split using x-axis is done, the left behind all the points that have an x-axis value less than the split value, the right tree having all values greater than the same one. The KD trees prove useful for variety of query types such as point and range queries. For this reason, they are important member of Lucene's indexing capabilities. This figure shows an example of a KD tree. Lucene implementation uses block KD, BKD tree, which is an efficient version that is IO friendly and restricts IO usage. Here you can see A is connected to B and C, and C is connected to D, and D is connected to E and F. Here you can see a BKD tree in spatial indexing. BKD trees are built in the same manner as KD trees, recursing and partitioning the n-dimensional space and performing an equal split at each recursion. However, BKD trees stop recursing once there are fewer than 1024 points. At that point, all points are written to one block on the disk. When a point is indexed in the BKD tree, it is converted into an equivalent byte array representation. Lucene then buffers the points being indexed and then writes them to using a points format. All default Lucene codecs now support the points being indexed. As evident in this figure, a BKD tree is a KD tree with B tree incorporated into it. Nodes have compressed keys and their children define key ranges with equivalent pointers to their children. You can see here the BKD tree. Here you can see a Lucene 9.5 file format. Here the index structure overview. Here you can see the index structure overview in Lucene 9.5 file format. Each segment index maintains the following. Segment info. This contains metadata about a segment which has the same number of documents, what files it uses, and information about how segments is stored. Field names. This contains metadata about the set of named field used in the index. Stored field values. This contains each document a list of attributes value pairs where the attributes are field names. These are used to store auxiliary information about the document such as title, URL, or an identifier to access databases. The set of stored fields are what is returned for each hit when searching. This is keyed by document number. The term dictionary, a dictionary containing all of the returns, all of the terms used in all index field of all the documents. The dictionary also contains a number of documents which contain the term. The pointers to the term frequently are proximity data. Term frequency data for each term in the dictionary, numbers of all documents that contain that term, the frequency of the term in the document unless frequencies are omitted, index_docs. Term proximity data for each term in the dictionary, the position of the term occurs in each document. Note that this will not exist all fields in the all document omit position data. Normalization factors, for each field in each document the value is stored that is in multiplied into score it for hits on that field. Term vectors, each field in each document, the term vector, sometimes called document vector, may be stored. The term vector consists of terms text and terms frequency. To add the term vectors to your index, see the field constructors. Per document values, like stored values, these are also keyed by document number but are generally intended to be loaded into the main memory for fast access, whereas the stores values are generally intended for summary result for searches. Per document values are useful for things like scoring factors. Live documents, an optional file indicating the document, which document is live. Point values, the optional pair of fields recording dimensionally index field to enable fast numeric range filtering and large numeric values like big integer and big decimal, 1D and geographic shape intersection, 2D and 3D. Vector values, the vector normal format stored numeric vectors in a format optimized for random access and of computation, supporting high dimensional nearest neighbor search. Here the class Lucene 90 segment info format in package org.apache lucene.codex. Lucene 90, the Lucene 9.0 segment info format. Here the class Lucene 9.94 field info format in package org.apache lucene.codex.lucene 94. Lucene 9.0 field info format. Class Lucene 90 stored field format in package org.apache lucene.codec.lucene 90. Lucene 9.0 stored field format. Class Lucene 90 posting format in package org.apache lucene.codex.lucene 90. Lucene 5.0 posting format, which encodes posting in a packed integer blocks for fast decode. Class Lucene 90 posting format in org.apache.lucene.codex.lucene 90. The Lucene 5.0 posting format, which encodes posting in a packed integer block for fast decode. Class Lucene 90 posting format in package org.apache.lucene.codex.lucene 90. Lucene 5.0 posting format, which encodes posting in a packed integer block fast decode. Class Lucene 90 forms norms format package in package org.apache.lucene.codex.lucene 90. Lucene 9.0 is score normalization format. Lucene 9.0 term vector format in package org.apache.lucene.codex.lucene 90. The Lucene 9.0 term vector format. Class Lucene 90 doc values format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 doc values format. Class Lucene 90 live docs format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 live doc format. Class Lucene 90 points format in package org.apache.lucene.codex.lucene 90. Lucene 9.0 point format, which encodes dimensional values in a block KD tree structure for fast 1D range and in dimensional shape intersection filtering. Lucene 95 HNSW vectors format in package org.apache.lucene.codec.lucene 95. Lucene 95 vector format, which encodes numeric vector values and optional associated graph connecting the document having values. The graph is used to power HNSW search. The format consists of three values: .vect file, .vex file, and .vem file. Here you can see the structure segment info field value stored field value, term dictionary, term frequency data, term proximity data, normalization factors, term vectors, per document values, live documents, point values, and vector values. Here you can see the summary of file extension in Lucene 9.55 format. Following table, this table summarizes the name and extension of the files in Lucene. Lucene file names by extension. Here the name segment files, extension segment _n. It stores information about commit point. Log file, write.log here. Write log prevents multiple index writers from writing the same file. Segment info stores metadata about the segment. Compound file, an optional virtual file consisting of all the index files for systems that frequently run out of file handles. Fields stores information about the fields. Field index contains pointers to field data. Field data stored fields for documents. Term dictionary, the term dictionary stores term info. Term index, the index into the term dictionary. Frequencies contains a list of docs which contain each term along with frequency. Positions stores position information about where the term occurs in the index. Payload stores additional per position metadata information such as character offset and user payload. Norms encodes length and boost factors for docs and fields. Per document values encodes additional scoring factors or other per document information. Term vector index stores offset to the document data file. Term vector data contains term vector data. Live documents info about what documents are live. Point values hold index point. Vector values hold index vectors. .vect files contain the raw vector data and .vem the vector metadata. Example, we can consider package org.apache.lucene.index. This is a code to maintain and access indices. As an example 2, we can consider this code segment here, index writer, class index writer, and index writer create and maintains an index. Here the index writer config holds all the configuration that is used to create index and index writer. Once index writer has been created with this object, changes to this object will not affect the index writer instance. For that, use live index writer config that is returned from the index writer get config index writer get config. And here you can see add document method. This adds a document to index, and index close all open resources and releases the write lock. And this index writer class is in the package org.apache.lucene.index. Here you can see the class fields provides the terms index for fields that have it and list which fields do. This is primarily an internal experimental API, C fields producer, although it is also used to expose the set of term vectors per document. This is in package org.apache.lucene.index. In index reader is an abstract class providing an interface for accessing a point-in-time view of an index. Any changes made to index via index writer will not be visible until new index reader is opened. It is best to use directory reader.open index writer to obtain an index reader if your index writer is in process. When you need to reopen to see any changes in the index, it's best to use directory reader.open if changed directory reader, since a new reader will share resources with previous one when possible. Search of an index is done entirely through its abstract interface, so that any class which implement is searchable. Here you can see the method of index reader get term vectors. This retrieves term vectors for this document, or null if term vectors were not indexed. Here access index field for an index segment, and here access term vector fields for a specified document. Here this code segment is related to terms. Terms, the class term access to terms in a specified field. Here has positions returns the true if the documents in this field store position. Here has offsets returns true if the document in this field store offsets. Has payloads returns true if the document in this field store payloads. Here the terms enum iterated to seek or step through terms to obtain frequency information for the current term. Here the iterator returns an iterator that will step through all terms here. Here in the next here in the byte ref represent byte array that as a slice offset plus length into an existing byte array. The bytes member should never be null. Use empty underscore bytes if necessary. Here in next increment the iteration to the next bytes ref in the iterator, returns the resulting byte ref or null if the end of the iterator is reached. Returns the resulting byte ref and or null if the end of the iterator is reached. The return byte ref may be reused across all next across call to next. After this method returns null, do not call again. The results are undefined. Here in the term returns the current term. So here we are getting metadata about the field here, position, offset, payload, and iterate through the terms here. And the class term is in the package org.apache.lucene.index. Here term represent the collection of terms within a field, exposes some metadata and statistics, and the API for enumeration. Here with the documents, here you can see the post class posting enum is a variable, iterates through the postings Not you must first call the doc id set iterator dot next doc before using any of the per doc methods. This is in the package org.apache.lucene.index. The posting enum is an extension of doc id select set iterator that iterates over a list of documents for a term along with the term frequency within that document. With regarding positions, here you can see a class posting enums iterate through the postings. Not you must first call doc id set iterator dot next doc before using any of the pre-doc methods. Posting enum also allows iteration of positions. A term occurred within the document. Any additional per position information, offsets, and payloads. The information available is controlled by flags passed to term enum postings. This postum enum is in package org.apache.lucene.index. As an example 7, we can consider this one. This is from Rabbit Talk. This following index definition would allow using Lucene index for this query. Org supports Lucene based indices to support both property constraint and full text constraint. Depending on the configuration of a Lucene index, can be used to evaluate property constraint, full text constraints, or path restrictions and shorting. You can see the query here. This index definition would allow using Lucene index for this query. The index definition node for Lucene based index must be of type query index definition, must have a type property set to Lucene, must contain the async property set to value async. This is what send the index update process to background thread. Note that compared to property index, Lucene property index is always configured in async mode, hence it might lag behind the reflecting the current repository state while performing the query. Here as an example 8, you can see the index reader here, the class index reader. Index reader is an abstract class providing an interface for accessing a point in time view of an index. Any changes made to the index via index writer will not be visible until new index read is opened. It is best to use in directory read dot open index writer to obtain an index reader. If your index writer is in progress, when you need to reopen to see changes in the index, it's best to use directory reader dot open if change directory reader, since the new reader will share resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that any subclass which implement is searchable. This is in package org.apache.lucene.index. This is open existing index here. As an example, now we are considering index writer in index APIs in package org.apache.lucene.index. Index writer is used to create an index and to add, update and delete documents. The class index writer in package org.apache.lucene.index, and index writer creates and maintains an index. Index writer is used to create an index and to add, update and delete documents. The index writer class is thread safe and enforces a single instance per index. Creating an index writer creates a new index or open an existing index for writing in a directory depending on the configuration of index writer config. A directory is an abstraction of typically represent a local file system directory. Various implementation of FS directory, but it may also stand for some other storage such as RAM. Now we are considering field types. Stored field values are retrieved by a searcher using implementation of stored field visitor. Class stored field visitor in package org.apache.lucene.index provides a low level means of accessing the stored field values in an index. Lucene supports a variety of different documents field data structures. Lucene's core and inverted index is comprised of postings. The posting with their term dictionary can be thought of as a map that provides efficient lookup given a term, roughly a word or token, to ordered a list of documents containing that term codex. Additionally, record impacts alongside posting in order to be able to skip over low scoring documents at the search time. Posting do not provide any way of retrieving terms given a document short of scanning the entire index. Stored fields are essentially the opposite of postings, providing efficient retrieval of field values given a doc ID. All stored field values for a document are stored together in a block. Different types of shorted stored field provide high-level data types such as strings and numbers on top of underlined bytes. Stored field values are usually retrieved by searcher using implementation of stored field visitor. Doc values field are what are sometimes referred to as columnar or column style fields by analogy to relational database terminology, in which documents are considered as rows and fields and columns. Doc values fields store values per field. The value for every document is held in a single data structure, providing for rapid sequential lookup of a field given a doc ID. These fields are used for efficient value-based sorting and for faceting, but they are not useful for filtering. Point values represent numeric values using a KDT data structure. Efficient one and higher dimensional implementation make these the choice for numeric range and interval queries and geospatial queries. Now we are considering fields in postings API. Field is the initial entry point into the posting API. This can be obtained in several ways. The class fields in package org.apache.lucene.index provide a terms index for fields that have it and list which fields to. This is primarily an internal or experimental API, although it is also used to expose the set of term vectors per document. Here the fields implement Java iterable interface. So it's easy to enumerate a list of fields here. Here the access index fields for index segment. Here the access term vector fields for specified document. So enumerate list of fields. Access the terms for this field. Here you can see terms. The terms represents collection of terms within a field, exposes some metadata and statistics and API enumeration. The class terms in package org.apache.lucene.index access to the terms in a specific field. Here the term enum provides an iterator over the list of terms within a field. Some statistic about the term and methods to access terms, documents, and positions. Here the metadata about the field. Here the iterate through term. Seek the specific term. Get the document frequency and enumerate through the documents, and enumerate through the documents and position. The documents now, the posting enum is an extension of doc_id settled iterator over the list of documents for a term along with the term frequency that within that document. Here the class posting enum in package.apache.lucene.index iterates through the postings. Note that you must first call the doc_id iterator, set iterator.nextdoc before using any of these pre-doc methods. Posting enum is an extension of doc_id iterator that iterate over the list of document of for a term along with the term frequency within that document. Positions postings enum also allows iteration of postings a term occurred within a document or any additional per position information, offset, and payload. The information available is controlled by flags passed to the terms enum postings. Now we are considering term statistics in index statistics. Term enum.docfreq method returns the number of documents that contain at least one occurrence of the term. This statistics is always available for an index term. Note that it will also count deleted documents when segments are merged. The statistics is uploaded as this deleted document are merged away. Term enum.total term freq method returns the number of occurrences of this term across all documents. Like docfreq method, it will also count occurrences that appear in the deleted documents. Now we are considering introduction in Apache Lucene index file format in package.apache.lucene.codex.lucene95. This here we are defined the index file format used in this version of Lucene. If you are using different version of Lucene, please consult a copy of the docs that was distributed with the version you are using. Now we are considering definition document numbers in definition. In particular, numbers may change in the following situations. Internally, Lucene refers to documents by an integer document number. At first, the document added to an index is numbered 0, and each subsequent document added gets a number 1 greater than the previous. Note that the document number may change, so caution should be taken when storing these numbers outside the Lucene. In particular, numbers may change in the following situations. A number is stored in each segment are unique when within the segment, and must be converted before they can be used in a larger context. The standard technique is to allocate each segment of range values based on the range of numbers used in the segment. To convert a document number for a segment from segment to external value, the segment-based document number is added. To convert an external value back to the segment-specific value, segment is identified by the range that external value is in. The segment-based value is subtracted. For example, 2, 5 document segment might be combined so that the first segment has the base value of 0 and the second of 5. Document 3 from the second segment would have been an external value of 8. When the documents are deleted, gaps are created in the numbering. These are eventually removed as the index evolves through merging. Deleted documents are dropped when segments are merged. A freshly merged segment has thus no gaps in the numbering in its numbering. Now we are considering file naming. All files belongs to a segment have the same name with the varying extensions. The extensions correspond to a different file formats. When using a compound file format, default for all small segment, these files except for the segment info file and log file and deleted document file are collapsed into a single .cfs file. Typically, all segments in an index are stored in a single directory, although it is not required. File names are never reused. That is, when any file is saved to the directory, it is given a never before used file name. This is achieved using simple generations approach. For example, the first segment file is segment _1, then segment _2, etc. Generation is a sequential long integer represented in alphanumeric base 36 form. Now we are considering log file. If the directory is different from the index directory, then the write log will be named xxx-write.log, where xxx is a unique prefix derived from full path to the index directory. The write log, which is stored in the index directory by default, is named write.log. If the log directory is different from the index directory, then the write log will be named xxx-write.log, where the xxx is a unique prefix derived from the full path to the index directory. When this file is present, a writer is currently modifying the index, adding or removing documents. This log file ensures that only one writer is modifying the index at a time. Now we are considering Lucene 9.7.0 Facet API. Lucene 9.7.0 Facet API provides facet indexing and search capabilities. Now we are considering index time joins in Lucene 9.7.0 join API. It's Lucene's join module. This query should be used after main query has been executed. For each hit, execute the parent children block join query. The class parent children block join query in package object lucene.search.join. This query that returns all the matching child documents for a specific parent document index together in the same block. The provided child query determines the matching child docs is been returned. The index time joining supports joins while searching, where joins document are indexed in a single document block using indexWriter.add documents. This is useful for any normalized content, XML documents or database tables. In database terms, all rows for a join table matching a single row is the primary table must be indexed in as a single document block. With the parent document being last in the group. When you are indexing this way, document in your index are divided into parent document, last document for each block. The child document, all others, you provide a bits set provider that identify the parent document, as Lucene does not currently record any information about doc blocks. At search time, the two parent block join query to remap join matches from any child query, that is a query that matches only child document up to the parent document space. Resulting query can be then used as a clause in any query that matches parent. If you care about what child documents matched for each parent document, then the parent children block join query to per matched parent document retrieve the child document that caused to match the parent document first place. This query should be used after main query has been executed. For each it executes the parent child children block query. So to map or join in the position direction, use two child block join query which wraps any query matching parent document, creating the joint query matching only child index. So this is basically with Lucene search module, but I included this here as an example due to the indexing. Do you see the importance of indexing here? Run the parent block join query to figure out top matching children nodes. Process top child hit. Now we are considering Lucene 9.7 memory API. Here the class memory index in package org.apache.lucene.index memory high performance single document main memory Apache Lucene full text search index in the package, and the memory API is for the memory, and the class memory index that's high performance single document main memory Apache Lucene full text search index. Here you can see an example usage. This class is a replacement. Here the memory index is a replacement subject for RAM resident directory implementation. It is designed to enable maximum efficiency for on-the-fly matchmaking, combining structure and fuzzy full text search in the real-time streaming applications such as NuxX query-based XML query, XML message queues, public subscribe system for blog newsfeed, text chat, data acquisition and distribution systems, application level routers, firewall and classifiers, etc. Rather than targeting full text search in infrequent queries over huge persistent data achieved historic search, this class target full text search of a huge number of queries over comparatively small transient real-time data, prospective search, for example as in here. This instance can hold the most Lucene document. With the document containing 0 or more field, each field having this name and full text value. Full text is tokenized, split and transformed into 0 or more index terms, also known as words on add field, according to the policy implemented by the analyzer. For example, Lucene analyzers can split on white space, normalize to lower case for case sensitivity, ignore common terms with the little discriminatory value such as he, in, and stop words, reduce the term to their natural linguistic root from such as fishing being reduced to fish, stemming, resolve synonyms, inflections, the sauri, tertiary upon indexing and or querying, etc. Abstract Lucene queries can be run against this class. Note that the Lucene query select on the field names and associated index tokenized terms, not on the original full text. The latter are not stored but rather thrown away immediately after tokenization. Now we are considering class index splitter in package lucene.misc.index. Here we are considering Lucene 9.7.0 miscellaneous API. Miscellaneous tool. The MAIC package has various tools for splitting, merging indices, changing norms, finding high-freq terms, and others. With the class index splitter, command line tool that enables listing segments in an index, copying specific segment to another index, and deleting segments from index. Now we are considering Lucene 9.7.0 replicate API. The provides index files replication capabilities. Here an example usage of replicator. The interface replicator is in package Lucene.replicator duplicated. Use log.apache.lucene.replicator.nrt instead. An interface for replicating files allows a user or allows a producer to publish revisions and consumers to check the updates when the client needs to be updated. It is given a session token through which can obtain the files of that revision. After the client has finished obtaining all the files, it should release the given session so that the files can be reclaimed if they are not redeemed, if they are not needed anymore. Files, this is a file replication. Here this package is a file replication framework. A replicator allows republishing replicating files between server and client. Producer publish revisions and consumes update to the latest revision available. Replication client is the helper utility for performing update operation. It can be invoked either manually or periodically by starting an update thread. HTTP replicator can be used to replicate revisions by consumers that reside on a different node than the producer. The replication framework supports replicating any type of files with the built-in support for single search index. An application should publish an index revision and the index replicator handler to the client. On the client. For an index and taxonomical pair, the application should publish an index and taxonomical revision and set index and taxonomical replication handler on the client. When replication client detects that there is new revision available, it copies the files from the revision and then invoke the handler to a complete operation. For example, copy the files to the index directory, fsync then, reopen and index read, etc. By default, only files that do not exist in the handler current revision files are copied. However, it can be overridden by extending the client. Example usage of the replicate is here. So here the server side, writer used for indexing. Client side, either local replicator or HTTP replicator if the client and server are on different nodes. Callback invoke after handler finish handling a revision and, for example, can reopen the reader. Can also be null if no callback is needed. Invoke a client manually or periodically. Check for update every 100 milliseconds. We are now considering tools. Type this command to launch Luke. Lucene Toolbox GUI tool, a swing app for browsing documents, is index terms and posting list, searching an index and so on. Type this command to launch Luke. So we can consider index format to old exception, the class. This exception is thrown when Lucene detects an index that is too old for this Lucene version. This is in package org.apache.lucene.index. As an error example, we can consider this one. Java IO exception, no subfile, sub-file with id.fnm found, etc. And here com.library.portal.search.lucene index writer.update document, etc. And here the org.apache.lucene.index.field infos, etc. And here you can see the compound find read also. Now we are focusing on Lucene storer. org.apache.lucene.store defines an abstract class for storing persistent data, the directory, which is a collection of name files written by an index output and read by an index input. Multiple implementations are provided, but fs directory is generally recommended as it tries to use operating system disk buffer caches efficiently. Here you can consider a package org.apache.lucene.store binary IO API used for all index data. Here you can see the fs directory class, base class for directory implementation that store index files in the file system. Here method public static fs directory open path creates an fs directory instance, trying to pick the best implementation given the current environment. The directory returned uses the native fs log factory The directory is created at the named location if it does not yet exist. This class is in package org.apache.lucene.sto. As an example 3, we can consider lucene.store.type equal JDBC. This is in Sun Glassfish web space server 10.0. There is a single property called lucene.store.type. By default, this is set to go to the file system. You can change this to this so that the index is stored in the database by making it the following here. As an exception example, we can consider class lockObtain failed exception. This exception is thrown when the write.lock could not be acquired. This happens when a writer tries to open an index that another writer already has open. This is in package org.apache.lucene.sto. As an exception example, we can consider lockObtain failed exception. Class lockObtain failed exception. This exception is thrown when the write.lock could not be acquired. This happens when the writer tries to open an index that another writer already has open. This is in package org.apache.lucene.sto. As an error example, we can consider this one, java.line.error. Unresolved compilation problems. Directory cannot be resolved to a type. The main method open path in the type fs directory is not applicable for arguments file. Now we are focusing on indexed files. An index file is a computer file with an index that allow easy random access to any record given its file key. Here you can see a detailed look inside the Lucene's index format. Here .fnm, the fields, stores information about fields here, and .tis, term infos, part of the term dictionary stores term info, and here .frq, frequencies, contains a list of docs which contains each term along with frequency, and .prx, positions, stores position information about where a term occurs in the index. Here in the inverted index, Lucene uses a well-known index structure called inverted index. Quite simply, and probably unsurprisingly, the inverted index is an inside-out arrangement of document in which terms take center stage. Each term refers to documents that contained it. Let's dissect a sample book data index to get a deeper glimpse at the files in the index directory. Regardless of whether you are working with a RAM directory or FS directory or another directory implementation, the internal structure is a group of files. In a RAM directory, the files are virtual and live entirely within RAM. An FS directory literally represents the index of a file system directory as directory. The compound file mode adds an additional twist regarding the files in a directory. When an index writer is set for a compound mode, the files are written to a single .cfs file, which alleviates the common issue of running out of file handles. Our summary glosses over most of the intricacies of data compression used in the actual data representation. This extrapolation is helpful in giving you a feel for structure instead of getting caught up with miniature, which again are detailed on Lucene's website. This figure represents a slice of a sample books index. The slice is a single segment. In this case, we have an optimized index with only single segment. A segment is given in a unique file name prefix _c in this case. Here field names .fnm. The .fnm file contains all the field names used by documents in the associated segment. Each field is flagged to indicate options that were used while indexing. Is it indexed? Does it have a term vector enabled? Does it store norms? Does it have payloads? In order of the field names, the order of the field names in the .fnm file is determined during the indexing and isn't necessarily alphabetical. Each field is assigned a unique integer field number. Each field is assigned a unique integer, the field number, according to the order in the file. In this file, that field number instead of string name is used in other Lucene files to save space. All terms, this is a term dictionary .tis or .tii file. All terms, tuples of fields, field name and value in a segment are stored in the .tis file. Terms are ordered first alphabetically. According to the UTF-16 Java character by field name and then by the value within the field. Each term entry contains its document frequency. The number of documents that contain this term within the segment. In this figure shows only the sampling of the terms in our index, one or more from each field. Not shown is the .tii file, which is a cross-section of the TIS file designed to be kept in the physical memory for random access to the TIS TIS file. For each term in the TIS file, the the .frf file contains entry for each document contained in the term. Here in our sample index, 2 books have the value JUnit in the content field. Term frequencies. The term frequencies in each document are listed in the .frq file. In our sample index, that for example ant in action document ID 5 has the value JUnit once in the content field. JUnit in action second edition has the value JUnit twice, provided once by the title field and the once by the subject field in this example. Our contents field is the aggregation of title, subject and author. The frequency of a term in a document in a document factors into score calculations and typically boosts a document relevance for higher frequencies. For each document listed in the .frq file, the positions.prx file contains entries for each occurrence of the term within the document. The term positions, the .prx file lists the positions of each term within a document. The position information is used when queries demanded it, such as praise queries and span queries. Position information for tokenized fields comes directly from the token position increment designated during analysis. This file also contains payloads, if any. In this figure shows 3 positions for each occurrence of the term JUnit. The first occurrence is in document 5 in position 9. In the case of documents 5, the field value after analysis is Ant Action, Apache, Jakarta, Ant Build, Tool, Java, Doc Development, JUnit, Eric, Hatcher, Steve, Logan. We use the standard analyzer, thus step word in Ant in action, for example, are removed. Document 6, JUnit in action, second edition has contents field containing the value JUnit twice, once position 1 and again position 3. Stored fields. When you request that a field to be stored, field.store.ers, it is written into 2 files, the .fdx file and the .fdt file. The .fdx file contains simple index information which is used to resolve document number to extract position in the .fdt file for the document's stored field. The .fdd file contains the contents of the fields that were stored. Term vectors. The term vectors are stored in 3 files. The .tvf file is the largest and stores specific terms stored alphabetically and other fields. Other frequencies plus the optional offsets and positions for the terms. The .tvd files list which fields had term vectors for a given document and indices byte offsets into the .tvf file so specific fields can be retrieved. Finally, the .tvx file has index information which resolves the document numbers into the byte positions in the .tvf and tvd files. Norms. The .nrm file contains normalization factors that represent the boost information gathered during indexing. Each document has 1 byte in this file which encodes the combination of documents boost, that fields boost, and normalization factor based on the overall length of the content that in that field. Deletions. If any deletions have been committed to the index against document content in the segment, there will be a .del file present, name _x_n.del, where x is the name of the segment and n is the integer that increments every time new delete are committed. This file contains a bit vector that set for any deleted documents. Here you can see the index structure in here. Here the index an index is basically a set of documents that are to be searched. The index may be composed of multiple sub-indexes or segments. Each segment is a fully independent index which could be searched separately. Fields, when a document is added to an index, different sections of the document are identified and given a common name called fields. For example, document title, document body, hyperlinks, the document URL, etc. Terms, the words in the field are extracted and are stored in the index as terms. A term basically a string extracted from the document. The same string in two different fields is considered different term. Terms are represented as a pair of strings. The first naming the field and the second naming the text within the field. Stored or indexed, the Lucene fields may be stored, in which case their text is stored in the index literally in a non-inverted manner. Fields that are inverted are called indexed. The fields may be both stored and indexed, tokenized and or non-tokenized. The text of the field may be tokenized into terms to be indexed, or the text of a field may be used literally as term to be indexed. Most fields are tokenized, but sometimes it is useful for certain identifier fields to be indexed literally. Lucene uses file extensions to identify different parts of the index. Here you can see the index structure. Here we are considering Lucene 3.4. Here segments are in index. Segments consist documents here. Documents are in segments. Here the fields are in a document, and here the terms are in field. Here you can see the now we are considering field information .fnm. Field info file with the suffix fnm records the index time attributes and field names for every field. Fields are numbered by their order in this file. Thus the field 0 is the first field in the file. Thus the field 0 is the first field in the file. Field 1 the next, and so on. Note that the like document numbers, field numbers are segment relative. Here you can see fnm version vint indexes version from 2.9 to 3.3 is -2, and indexes version for more than 3.4 plus is -3. Next we can see the field count vint, and next field name field bits. Here field name is string. In this this section consists of field name string and field bits byte. Here the bit 8 is 1 equal positions are omitted for the index field. Bit 7 1 equal term frequencies and positions are omitted for the indexed field. Bit 6 1 equal payload are stored for the index field. Bit 5 the 1 equal norms are omitted for the index field. Bit 4 1 equal terms offsets are stored with the term vectors. Bit 3 1 equal term positions are stored with the term vectors. Bit 2 with term vectors equal 1 and without term vector equal 0. Bit 1 indexed field equal 1, non-indexed field equal 0. So this bit 8 to bits 1 are in field bits byte. The field name string and field bit string are in this section. Here you can see stored fields. Stored fields are the original raw text values that were given in Lucene. This is not really a part of inverted index structure. It's simply a mapping from document ID to stored field data. Stored fields are represented by two files. The field index or FDX file that contains for each document a pointer to its field data. The field data or FDT file this contains the stored fields of each document. Here you can see the field index of FDX file .fdx. Here the offset equal doc id multiplied by htail u int 64 size. Here the field value position here the field value position segment size. Here the field value position u int 64. Doc id is field value. It is connected to field data or FDT file. This should be FDT here. Here you can see document field data segment size here, and here the before that here you can see field count v int and another field, and then here you can see field number v int, and in this section consists of field number v int and bits v byte, and it consists bit 8 bit 8, and here the bit 7 to bit 6. So here bit 7, and here the bit 6 to and bit 5 and bit 4 is 001 value is an int, and 010 equal value is a long, 011 is equal value is int as float, and 100 the value is long as double. The bit 3 is in bit 3 one equal field has compression option enabled, only available for version less than or equal 2.9.x. Bit 2 one equal field contains binary data. Bit 1 tokenizer field equal 1 and non-tokenizer field equal 0. So it will be here bits and bits byte. Here the value string or binary value or int, long depending on bits 4 to 6, with the binary value here value size v inc, here the here the value size binary value, the value size v int, and byte is value size. But here the field name, bits and value here with the field count here, and then this section represents this area, and then the document field data segment size here. Now we are considering here you can see the term dictionary. The term dictionary stores how to navigate the various other files for each term. At simple high level, the term dictionary will let you where to look in the FRQ and PRX files. For further information related to that term, terms are stored in an alphabetical order for fast lookup. Further, another data structure, the term info index, is designed to be read entirely into memory and used to provide random access to the TIS file. Other bookkeeping, skip test, skip list and index intervals also tracked with the term dictionary. Term infos.tis, the term infos file.tis contain all terms in a segment ordered by field name, then the value within the field, it also contains document frequency for each term, inverted index, so how many documents contain that term. Term info index TII .tii, this contains every index interval entry from the TIS file along with its location in the TIS file. This is designed to be read entirely into memory and used to provide random access to the TIS file. The structure of this file is very similar to the TIS file, with addition of one item per record in index delta. Index interval. In order to accelerate the searching of a term, Lucene uses multi-level skip list. The index interval is the interval at which the terms are saved in the .tii file. For example, assuming index interval equal 4, the dictionary index .tii a file will save 4th, 8th, 12th term, which can speed up the dictionary lookup in TIS. Skip interval. Skip interval is the fraction of term docs stored in skip tables. It is used to accelerate term docs .skip to int. Larger values result in small indexes, greater acceleration, but few accelerable cases, while smaller value result in bigger indexes, less acceleration in case of small value for max skip levels, and more accelerable cases. Max skip levels in the max number of skip levels stored for each term in the .frq file. A low value result smaller indexes but less acceleration. A larger value result in slightly large indexes but great acceleration. See format of .frq file for more information about skip levels. Prefix length. The term text prefixes are shared. The prefix length is the number of initial characters from the previous term, which must be pretended to a term suffix in order to form the term's text. Thus, if the previous term's text was born, then the term is boy. The prefix is prefix length is 2 and the suffix is y. Document frequency. Docfreq is the count of the document which contain the term. Frequency delta. Freq delta determines the position of this term's term freq within the .frq file. In particular, it is the difference between the position of terms data in that file and the position of the previous term's data, or 0 for the first term in the file. Proxy delta. Prox delta determines the position of this term's term position within the .prx file. In particular, it is the difference between the position of the term's data in that file and position of the previous term's data, or 0 for the first term in the file. Skip delta determines the position of this term's skip data within .frq file. In particular, it is the number of bytes of the term freq and that the skip data starts. In other words, it is the length of the term freq data. Here you can see the term infos .tis. Here the TI version, uint 32, term count uint 64, index interval uint 32, skip interval uint 32, then max skip levels uint 32. Here term info, and then after gap term infos there. Here index intervals, one index interval here and then another index interval. Here this is index interval. Here term infos, term count. Term info consists of term, doc frequency, vint and frequency delta vint, proxy delta vint, and skip delta vint. Term consists of prefix length vint, suffixed string, and field name vint. The term info index .tii, TI version uint 32, index term count uint 64, index term count equal term count divided by index interval. Here term count L, index interval u int 32, then the skip interval u int 32, max skip levels u int 32, term index and term index, and there are term indexes, and this is term index count from this area. Term index consists of term info and index delta or v long. Here the term index is connected to term info here. Here the term index is connected to term info here, and term index connected to term info here. So term indexes are connected to term infos in term infos. Now here you can see term frequencies dot frq in Lucene 3.4 here. The dot frq file contains the list of document which contain each term along with the frequency of term in that document. This file contains the term posting list. This file contains the term posting list asterisk term count entries. Each entry is a posting list corresponding to a term. Each posting list consists of a term frequency and a skip list. Term frequency consists of a list of doc deltas and the number of times this term occurs in that doc. The doc delta encodes both the document number and the frequency. In particular, doc delta divided by 2 is the difference between this document number and the previous document number, or 0 when this is the first document in a term freq. When doc delta is odd, the frequency is 1. When the doc delta is even, the frequency is read as another vint. If omit tf equal false, store the term frequency. For example, if the term occurs once in the document 7, doc id equal 7, the freq equal 1, and 3 times the document 11, doc id equal 11, and freq 3, we would get the following sequence of v int 15, 8 and 3. Here's how it is calculated. In order to save space, Lucene does not store the doc IDs as is. Instead, it calculates the delta as a delta. Doc ID delta equals 7 and frequency equal 1. Doc ID delta equal 4, frequency 4, 11 minus 7, and freq equal 3. For this first term, since the frequency is 1, the frequency information is encoded in the delta itself. Doc ID delta equals 7, and the binary is 0000111. Since we want to store the frequency of 1 in doc delta, the last bit of the doc delta is 1, doc ID is odd, so we know that the frequency is encoded in the doc delta and freq equal 1. For the second term, since the frequency is more than 1, we use the separate vint to calculate the frequency. Doc ID delta equal 4 in the binary 00000100. Since we want to show the following int, so is for frequency and not another doc ID, we need to make the last bit 0. Then shifting left for and 1 by real frequency equal 3 then. So to get the sequence, doc delta equal 15, doc delta equal 8, freq 3, namely sequence 1583. If omit tf equal true, skipping storing term frequency. If the omit tf were true, it would be this sequence of vint instead 7 4. If we omit term frequency, then all we are storing is the doc deltas. The doc deltas are therefore doc ID 7, doc ID 11 equal to doc ID 7, doc ID 11 minus 7 is 7 and 4. Skip data. The skip data contains a set of skip lists that allow us to find term frequency, doc delta, freq quickly. Number of skip levels in skip data equal num skip levels. Equal min skip data equal num skip level equal mint max skip levels flow log doc divided by log skip level. Doc frequency equal doc count that contains the term item. Number of nodes in and each skip level equal doc freq. Number of nodes in each skip level is equal doc freq divided by skip interval to the power level plus 1, level equal level greater than or equal 0. All the skip levels are appended together, preceded by the skip level length. The last level does not need skip level length since there are no more levels below it, so it is skipped. All skip datum in all levels except the last level have a skip child level PTR. Which point to the next skip level. Each skip datum skip node contains the following information: document number, payload length, freq skip, proxy skip, proxy skip and skip child level PTR. Here you can see term frequencies.frqs file. Here the term frequent skip and skip data with term count here, and here the it consists this one consists of term freq, doc freq, and here the skip data. Here the term freq consists of doc delta vint and frequent, then frequency vint. Here the skip data consists of skip level, skip level length and skip level, num skip level -1, and skip level and skip datum. Here the skip level length vint and skip level, and it's connected to a skip level and skip datum here. Doc freq divided by skip interval to the power level +1 here. Here the skip level and skip level is connected. This is skip level here. Here the skip datum. It consists of doc skip vint, payload length vint, is freq skip vint, proxy skip vint, skip child level pointer vlong, and here it's connected to here the skip data. Here the you can see the frequencies file with the skip list here. For example, if the skip interval is 4, equal max skip levels 2, and doc frequency is 35. The skip level 0 has 8 skip data entries. Equal 35 divided by 4 to the power 0 plus 1, containing the third, 7th, 11th, 15th, 19th, 23rd and 27th and 31st document numbers in term freqs. Skip level 1 has 2 skip data entries, equal 35 divided by 4 to the power 1 plus 1, containing the 15th and 31st document numbers in term freqs. Thus for skip level 4, and when there are 35 documents, skip level 0 should include documents 3, 7, 11, 15, 19, 23, 27 and 31, and skip level 1 should include 15, 31 documents. But in the real implementation, we store the previous docs as shown here. Here you can see doc freq 35 and skip level 4, and this is doc list, and here the skip level 0 and here skip level 1. Here the term here the frequencies .frq, term freq skip data term count here the freq term freq and skip data, and here doc freq, and this is a term posting list. Here the term freqs are there, and in the end here the skip data, and term freq has doc delta vint and frequency vint term freq, and here the skip data skip level length skip datum equal 14. Here the skip datum equal 13 the 30, skip datum 2, skip datum 6, skip datum 10, skip datum 14, skip datum 18, skip datum 22, skip datum 26, skip datum 30. Here mappings, and skip datum 2 here. and here is skip level 1, and here skip level 2. Skip level is equal 0 here. Here the skip level 22 skipped datum, doc skip vent, payload length vent, freak skip vent, proxy skip vent, and skip child level pointer belong. Here the now we are considering position location data.prx. The .prx file contains a list of positions that each term occurs at within the document. If omit tf is set to true in a field, no entry for that term will be stored in this file. If the omit tf is set for all terms, then the .prx files will not exist. The position delta is the is the difference between the position of the current occurrence in a document and the previous occurrence, or 0 if this is the first occurrence in the document. For example, term positions for a term which occurs at the 4th term in one document and as the 5th and 9th term in the subsequent document, the document would be the following sequence of vent 454. Payload in Apache Lucene is an arbitrary byte array stored at a specific position. That is a specific token divided by term in the index. A payload can be used to store weight for specific terms, so things like part of speech tags or other semantic information. Payload length is the length of the payload data. If there is no payload length but the payload data is found, its length is the same as the previous payload. Position file.prx, here the term positions, term count. Term positions consist of here term positions, here the positions, here the position doc freak, and position consist of positions consist of position, here the position freak. Position consists of doc position delta, vent, and payload, and payload consists of payload length, vent, payload data bytes, and here the frequencies file.frq, skip level length. This is skip level 1 here, skip level datum 14, skip level skip datum 30, and here the skip level 0 as an example. Skip datum 2, skip datum 6, skip datum equal 10, skip datum equal 14, skip datum is equal 18, skip datum is 22, skip datum is 26, skip datum is 30. Here the in this example here the position, this position is connected to skip datum 2, and this position is connected to skip datum 6, and sorry this skip datum 2 is connected to skip datum positions here, skip datum 6 position is connected to position here, skip datum is 14 is connected to position here, and here the skip datum 14 is connected to skip datum 14 is here, and skip datum 30 is connected to skip datum 30. Here you can see the .kdd in filed in Lucene 8.6.0. The data structure of .kdd is here. Leaf node data describe the information of a leaf nodes. You can see there is only leaf node data in .kdd file, and the default maximum number of points in each leaf node data is 512 and 512. Here you can see the .kdd file structure, header, then fields, then footer. The field consists of left node data, leaf node data, and leaf data and the data segments. Here you can see a leaf node data. The count describes the number of points in leaf node data. Doc IDs describe the set of document IDs which point in a leaf node data belongs to. Point values describe a set of point values. Each point value is split into point values describes a set of point values. Each point value is split into two parts: common prefixes and block packed values. Here you can see a leaf node data consists of count, doc IDs, and point values. Here you can see the common prefixes. Common prefixes describe the set of common prefixes with each dimension. Length value, the value describe the common prefix value with the byte, and the length means the length of a common prefix value, number of bytes. Here you can see common prefixes consist of dimensions, first, second, n dimension, and each dimension consists of length and a value. Here you can see here .kdi in Lucene 8.6.0. The data structure of .kdi file is here. Here the packed index value describes the information of all inner nodes, also known as branch node. Inner node has 4 types of data structure according to the position of in KD tree and its subnode. Right node has leaf child. Inner node, that is the right that the inner node is the right node of its parent node, and its child node are leaf nodes. Right node has not leaf child. The inner node is the right node, and its parent node and its child nodes are not leaf nodes. Left node has leaf child. The inner node is the left node, and its parent node and its child node are leaf nodes. Left node has not leaf child. The inner node is the left node, and it's of its parent node, and its child nodes are not leaf nodes. Root node as the inner node, and it belongs to right node has not leaf child. Here you can see it consists of this .kdi consists of header and fields and footer. Each field consists with the packed index value. Here you can see right node has not leaf child. Here the left leaf block FP describe the pointer where the position of the leftmost leaf node of the current inner node in the .kdd file is. Code describes the metadata about inner node, such as split dimension or byte per dimension, how many bytes each value in each dimension takes. Split value, in this stage the constructing a KD tree, that set of points in inner node will be split into 2 subnodes according to split value, which is a value of one of the dimension. left num byte describe the total size of one inner not left subtree. Here inner node has not left child consists with left leaf block fp code split value and left num bytes. Here you can see right node has not leaf child. Left is in the here the left leafed block fp here the left leaf block fp code and split value describes the same meaning. Right leaf block fp describes a pointer where the position of the right leaf node of the current inner node in .kdd file is. Here the right node has left child consists with left leaf block fp code split value and right leaf block fp. Here you can see left node has leaf child. You can see the code the split value and right leaf block fp describe the same meaning. The left node has leaf child consist code split value right leaf block fp. Here you can see the left node has not leaf child. Code split value and left num bytes describe the same meaning. Left node has not leaf child consists code split value left num bytes. Here the you can see the here you can see the KD tree and index values index file. Inner node in a KD tree would be stored in .kid file as below. KDI file as below. Here you can see the root node and it's connected to inner nodes, and this node is connected to other inner nodes, and this is these are leaf nodes. Here the root node is connected to right node has not leaf child. Then the this inner node is connected to left node has not leaf child. This inner node is connected to left node has leaf child, and this one is connected to right node has leaf child, and this inner node is connected to right node has not leaf child. Here the left node has leaf child and the right node has leaf child. Here the this section makes a packed index value in .kdi in packed index value which is a field in .kdi file. Here you can see header and fields and the footer. Here you can see the leaf node in leaf node in .kd tree would be stored in kdd file as below. As here you can see a root node, and you can see inner nodes here, and then these are leaf nodes here. Here this leaf node is connected to left node data, and this one is connected to left node data. Leaf node, sorry, this one is connected to leaf node data, and this is connected to this leaf node data, and these leaf nodes are connected to leaf node data here, and this segment is this segment is a field in .kdd file. You can see header here and fields here and footer here. Here you can see the left num bytes. The left num bytes describe the total size of one inner node's left subtree. It makes a reader can skip to the position of inner node's right node in .kid file, and its left node is just in the next position. Here you can see a root node, and these are inner nodes, and you can see leaf nodes here. Here the root node is connected to left node has not leaf child, and it consists of left leaf block FP code, split value, and left num bytes. Left num bytes are here, there, here. Here the this node is connected to leaf node has not leaf left node has not leaf child leaf child. This one is connected to this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child, and this one is connected to this inner node is connected to right node has not leaf child, and this inner node is connected to left node has leaf child, and this inner node is connected to right node has leaf child. And here the left num bytes is covered this size, the left num bytes here for the tree here. Here you can see the root node is connected to right node has not leaf child, and this inner node is connected to left node has not leaf child. This consists code, split value, and left num bytes. So it's covered this left here the left num bytes here, this section, and here the inner node is connected to leaf node has leaf child, left node has leaf child, and here this inner node is connected to right node has leaf child, and this one inner node is connected to right node has not leaf child, and inner node is connected to left node has leaf child, and inner node is connected to right node has leaf child. Here you can see left leaf block FP and right leaf block FP in Lucene 8.6.0 here. By left leaf block FP and right leaf block FP leaf nodes can be positioned in .kdd file. Here you can see the root node is connected to right node has not leaf child, and it consists of leaf left lead block FP, chord, split value, and left num bytes, and it is connected to then here the left leaf block FP is connected to here the left leaf node data here, and here the here you can see this inner node is connected to leaf node has leaf child, sorry, left node has leaf child, and is chord, split value, and right leaf block FP is connected to this one here, this leaf node data here. Here you can see the this inner node is connected to right node has leaf child, and here you can see left leaf block FP, chord, split value, and right leaf block FP. Here the left leaf block FP is connected to this leaf node data, and here the right leaf block FP is connected to leaf node data here. Here you can see the .kdm is the data, the data structure of .kdm file. Data structure of .kdm file is here you can see here the -1 is a fixed padding value. In this stage, the reading in the stage of reading .kdm file, it has a mark. It as a mark means the means all fields has been read. Here you can see a .kdm file consists of header and fields, and -1 here, and KDI file length, and KDD file length, and footer, and field consists of field number and index. Here you can see KDI file length and KDD file length. In this stage of reading .kdm index file, KDI file length and KDD file length used to validate KDI and KDD files, such as truncated file or file too long. Here you can see the .kdm file. It's it consists of header and fields, and -1 KDI file length and KDD file length and footer. Here KDI file length is connected to a KDI file length here. Header, the length of with header and fields and footer here in KDI, and KDD file length is connected to the KDD file length in file length in .kdd with header, fields, and footer. Here you can see in index. Here you can see the index in .kdm. Here you can see the header. It consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start FP, index start FP. Here you can see the index in .kdm here. Here num data dims describe how many dimensions we are storing at the leaf data nodes. Here the num index dims describe how many dimensions we are indexing in the internal nodes. Here count per leaf describe the maximum number of points in each leaf node. Byte per dim describe the number of bytes per dimension. Num leaves describe the number of leaf nodes. Min packed value describe the minimum value for each dimension, and max packed value describe the maximum value for each dimension values. Point count describe the total number of index points across all document. Doc count describe the total number of document that have index at least 1 point. Length describe the size of packed index value. Data start fp describe the pointer where the beginning position of current field data in .kdd file is, and index start fp describe the pointer where the beginning of position of current field data in .kdi file is. Here you can see the kdm .kdm, and it has header fields and -1 .kdi file length, .kdd file length, and footer. In the field you can see the field number and index here. Index consists of header num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length. Data start fp here with is connected to .kdd here, and here indexed start fp is connected to .kdi here, and here the .kdd has a header, fields and footer. Field has leaf node data segments. Here the index start fp is connected to .kdi. Here it has header, fields and footer, and field is a packed index value. Here you can see .kdm complete data structure here now. Here the .kdm consists of header and fields, -1 kdi file length, kdd file length, and footer. Field consists of field number and index consists of header, num data dims, num index dims, count per leaf, bytes per dim, num leaves, min packed value, max packed value, point count, doc count, length, data start fp, and index start fp. Here you can see the .kdd complete data structure. Here you can see the .kdd has a header, fields and footer. Field has leaf node data segments. Leaf node data consist count, doc IDs, and point values. Point value consists common prefixes and block packed values. Common prefixes consist dimensions, first, second, and in dimension here. Each dimension consists of length and value. Here you can see .kdi complete data structure. Here you can see the .kdi. It has header, fields and footer. Field is a packed index value, and packed index value consists of right node has not leaf left leaf child, and etc. Then left node has not leaf child, left node has leaf child, right node has leaf child, right node has not leaf child, etc. Then right node has leaf child. Here you can see the representation of inverted index. A linear scan is a simple process sequentially going through each line of in the system and checking its parameter, that is condition in a given query. This is precisely how Unix grep command works, and it also works fairly well with the wildcard and regular expressions. If the size of data set being searched size is not too large and then the hardware being used is reasonably powerful, linear search is the simplest way. However, linear search starts showing performance degradations beyond the a million median size document. The world around us is too experiencing an information explosion. In fact, the amount of data that needs to be processed to extract relevant information is quadrupled over last 10 years thanks to the advent of connected world, handheld devices and IoT. Linear search cannot be scaled to meet those needs, and so we need something more sophisticated and performant than that can handle massive dataset while still providing relevant result at reasonable speed. Linear searches also limit what kind of queries can be answered. For example, there is no way to define query that seeks close matches of a given pattern. Suppose, for instance, that we search for document with the words flower and sunshine within a proximity of 3 words in a document. Doing so with a linear search is impossible. So also there is no notion of rank result, that is a given query the result is either a match or not for a linear scan. If we want some sort of ranking, we cannot use the linear scan. An inverted index here is a data structure used to store data in an inverted manner. That is, terms are mapped according to mapped to documents in which the terms appear. Any unique term appearing in any document is made part of the inverted index. As shown in this figure, this data structure proves useful for answering questions like find me the document containing term 1 in an optimized manner. As you can see, a single term search is a constant time operation. To create an index file, fields within a document are first split and tokenized. A sorted list of all the unique terms is created. And the documents that contain the corresponding terms are populated. While being fast for a single term query, inverted indexes can also answer an important class of questions, similarity queries. Here you can see a term and document IDs, here book 1, book 2 and book 3. Here you can see Lucene index structure. The on-disk representation of Lucene index is optimized to be sufficient in reads and writes, and it allows searches into required areas of the index. At the heart of the Lucene lies the Lucene index file format. Post-Lucene 4 formats are pluggable using custom codecs and codecs. However, the default file format is what is published on Lucene's official website and what is in the referring to this figure. The basic component to start defining are as follows. Field definitions. Field definitions are stored in an independent file named field infos. with the extension fnm. From the with version 4.0 from the official definition, field infos.fnm is going to fnm version, fields count, then field name and field bits, field counts. Here you can see the term dictionary. The term dictionary is represented by two files. The term infos, the TIS file hold the metadata about the term, such as term name, skip information, and document frequency. That is the count of document that hold the term. The TIS file also hold the useful information that helps the Lucene to build structures for more optimal access of relevant document for a given term. Lucene uses skip data structures internally to make access faster. And this TIS file holds data to help the build this structure. In addition, metadata such as term frequencies in this file allows allows faster access to other files. The term infos index file, the TII, holds metadata to allow random access to the term infos file. The frequency file, the frequencies file extension .frq maps documents to a term. That is, it contains a list of all documents that contains a term present in the terms dictionary, along with the frequency of each term in the document. Positions file .prx, positions file extension .prx represent the list of positions at which each term occurs within the document. Here the field definition .ffnm file is connected to a posting list .tis. It is connected to a frequency .frq, and it is connected to a position here, the .prx. As we can consider this as an example here, the interface path, an object that may be used to locate a file in a file system. It will typically represent a file, dependent file path. Here you can see the class files. This class consists exclusively of statics methods that operate on files, directories, so other typical types of files here. This interface path is in module java.base and package java.nio.file. As an example 2, we can consider .nfm. The field names are stored in the field info file with suffix .fnm. 3, we are considering class index file names in package org.apache.lucene.index. This class contains useful constant representing file names and extensions used by Lucene, as well as convenience method for querying whether there are file name matches and extension, as well as generating file names from a segment name generation and extension, file name from generation, segment file name.